Yeah, good morning, everybody, to our SPCLB cast. A wonderful snowy morning here in Zurich. And I'm super happy that we could convince Peter Pietzuch to give a talk about, from Imperial College, to give a talk about security, which is actually of more and more importance in high performance computing. So we'll see what he's going to talk about. Thank you, Peter.
Peter is a professor of distributed systems at Imperial College London, where he leads the large-scale data and systems group and is also a co-director for Imperial's IX initiative in AI. His research focuses on the design and engineering of scalable, reliable, and secure data-intensive software systems, with particular interest in performance, data management, and security issues. Among other achievements, Peter was a chair of Eurosys and a PC chair for SOC 2023 and ICT-CS 2018. Before joining Imperial College London, he was a postdoctoral researcher at Harvard University and received his PhD from the University of Cambridge. Without further ado, the scene is all yours, Peter.
All right, fantastic. Thank you very much. Yeah, so good morning, everybody. So thanks a lot for the kind introduction and thanks a lot for having me here today. So let me share my screen. Okay, so can you see my slides?
Yes.
Fantastic. All right, yeah, so what I would like to talk about today is the work that we've been doing on really rethinking how to architect cloud software stacks so that they achieve higher security. And what we used in this particular work is a new hardware technology, which is memory capabilities. So we thought if the hardware provides this particular security-focused feature, how would it impact the software stack? So the work that I'm going to present is obviously done by a large team of people. So I just specifically want to give a shout out to Vasily Sartakov, who was the lead postdoc, and he implemented a lot of the systems that I'm going to talk about today. Okay, so the motivation for this work is really that most large-scale systems these days are deployed in cloud environments. And when you're deploying your software in a cloud environment, well, you must trust the cloud provider and the software stack that runs in that environment. And as we all know, those software stacks are really complex, right? So they're large, they consist of many layers, the firmware, the hypervisor, the operating system, various middleware layers. And that's what then supports your application. So if you're using a cloud environment, you kind of, well, you trust your application, you deploy this, but then there's this big, humongous stack. And the question that we wanted to ask is, well, how can we make this trustworthy? How can we improve the security of these types of cloud-based software deployments, avoiding the fact that we're running this large trusted computing base where we essentially just need to, well, trust the whole thing. So having a large TCB that you need to trust in this way is bad, right? So we all know about those examples of the size of those software stacks in literally millions and millions of lines of code, and large amounts of code in your TCB mean a lot of security vulnerabilities, right? And there's this steady stream of examples that we see where people find vulnerabilities in host operating systems and hypervisors and other parts of that stack that gives attackers vectors into the system, and that leads to a lot of security problems. So what we wanted to ask is, if we step back and we have the freedom to almost do a clean slate design for that cloud software stack, how would we do this? How would we do this differently? So when you think about this problem, you can think about what are the requirements that you have for a trustworthy cloud stack. So one aspect is that you need to isolate different components of your stack. And obviously compartmentalization is a very well understood and used security technique. So if you have, for example, a microservice architecture with a bunch of services, an analytics service, a storage service that you're deploying, they may be supported by respective guest operating systems running on a hypervisor. What you want is you want to isolate those different components from each other. And this way you're containing particular attacks within a compartment. And the other thing that we like is if those isolation guarantees are enforced by the hardware, because that makes it harder for an attacker to circumvent them. So we want isolation, but at the same time, we also want to share data efficiently between those components, right? So obviously our microservices need to communicate with each other. The microservices also need to interact with a guest operating system via system calls to execute I/O operations and so on. And the performance of this data sharing matters. So for example, the latency of particular calls into, say, the guest OS will then impact how, with what performance your application is going to execute. And then there may be more sharing that we want to do in the cloud environment, because a lot of the components that we deploy, they're often the same, right? So we may be running the same, Linux kernel as the guest OS. In our microservice deployment, we may have a lot of database instances, say, MongoDB, that is running everywhere, and the code is essentially duplicated. So ideally, what we would like to do here is share those components. So sharing is good because it can increase the memory density in the cloud, and cloud environments are all about consolidation, right? So this is something that cloud providers are quite keen on. So we also want to enable sharing of code across those different isolated compartments, at least in an ideal world. So you can now see that we are immediately introducing this tension that on the one hand, we want our trustworthy stack to isolate things with strong isolation guarantees, but then we also need to support this efficient sharing, which is, well, the opposite of isolation, because we're breaking down the isolation boundaries to exchange data efficiently. So how do we do this today? Well, today we rely on the MMU, the memory management unit, to give us memory isolation and sharing in most examples. So the MMU gives us memory pages in a virtual address space. It's a privileged entity, and it controls the visibility of those memory pages. So this gives us isolation, but it has the drawback that isolation now always has to happen at a page granularity. So if, well, you're exposing an entire page and there's some other data on that page, you may be exposing extra data. So you always now need to think about this particular granularity that you have. When you're sharing pages, you need to involve the MMU as a privileged layer, and that can carry an overhead, right? So therefore, for example, mapping pages, well, requires a kernel call, so you have to pay for that cost. So often you have a privileged intermediary, therefore, like the OS kernel, to set up shared buffers, and that adds an overhead. So there is essentially this MMU tax that we're used to paying when we build our virtualization solutions or other isolation mechanisms. So the two main ways how we've implemented this in cloud stacks are virtual machines as one way. So they give us strong isolation guarantees and a kind of smallish TCB where the privilege layer is the hypervisor that enforces that isolation. The drawback is that they are not great at sharing, right? So sharing usually means data serialization. You may be going through a network stack. And then whenever you want to interact with the hypervisor, you may have to pay costly hypercalls. So great at isolation, not that great at sharing. Containers, as the other technology, are kind of the opposite. So they're actually quite good at sharing because there's a shared OS kernel, and they essentially just do namespace isolation between the different compartments that you have. So they give you efficient inter-process communication, IPC mechanisms, but they are less good when it comes to the strength of the isolation because they rely on this really large TCB to implement namespace isolation. And the TCB here is, well, the Linux kernel, right? So a lot of lines of code. So what we wanted to ask, if we are doing this clean slate thing and we're redesigning a cloud stack, can we somehow combine strong isolation with efficient sharing and achieve all of this while not ending up with a very large TCB? Right, so that seems really challenging. So how do we approach this particular problem? Well, hardware to the rescue. right? So it is quite exciting what is happening in computer architecture, where it used to be the case that a lot of the new hardware features were all about improving performance. But now that we're sort of, well, out of ways how we can easily improve performance, you might as well use some of that silicon for new security features. And this is sort of what we have been seeing. Right? So there are examples like trusted execution environments, TEs, that are supported by modern general purpose CPUs that led to confidential computing. So they are a hardware security feature. On the RISC-V platform, we have things like PMP, physical memory protection, that can be used in quite flexible ways to implement new types of isolation solutions. And the particular hardware feature that we wanted to exploit is hardware support for memory capabilities as implemented using the CHERI ISA extension. And I'm going to talk much more about this. So, like, the way to think about memory capabilities is that essentially they allow you to ask the question, what if the hardware provided an efficient mechanism to share arbitrary sized memory regions between otherwise isolated entities? Which is sort of kind of what we want, right? So we want that strong isolation of arbitrary sized regions of memory, but we also want to be able to efficiently share them whenever we need to. And this is what capabilities ultimately give us. So what I'm going to talk about in the rest of the talk is the two pieces of work that we've done in terms of creating such a new trustworthy cloud stack using hardware memory capabilities. And I'll talk about one work that looks at the challenge of creating an abstraction for isolation and sharing. And that abstraction we called cVMs. So they are a bit like VMs in terms of the isolation that they give you, but they are entirely implemented using capabilities and not page table separation. And the other piece of work is org, which now takes those ideas further and thinks about how can we deduplicate memory efficiently using capabilities. So here we are looking for redundancy within that stack, and we're using this capability mechanism to then share components across otherwise isolated entities. Okay, so let's dive right into this. So I think with this audience, I probably don't need to say too much about what memory capabilities are, but the way to think about CHERI capabilities, they're essentially 128-bit fat pointers where the additional metadata associated with that pointer is bound information and also a richer set of permissions of how that particular memory can be accessed. So this is what gives us essentially a way of then referring to memory regions at a byte granularity, and those bounds and permissions are automatically enforced by the hardware. So therefore, there's sort of no software runtime cost that we're introducing if we, for example, did bounds checking manually. So just a small illustration with a regular memory access, if we are accessing a particular buffer in memory at a given offset, well, we can access the first byte of this particular buffer. If we then try to access an offset that goes beyond the end of that buffer, traditional hardware will happily allow us to access that memory because it doesn't constrain access within the bounds of the buffer. So this is obviously where bad things can happen with this kind of out-of-bound memory access. With capabilities, our pointer now also has essentially this bound, right? So there's now sort of a maximum associated with that pointer. So when we now use a capability instruction to dereference that particular pointer, and we provide an out-of-bounds access, well, this will be rejected by the hardware. So essentially, we get a memory fault because the hardware now understands that this is an invalid access that cannot be achieved using that particular capability. So the nice thing about architectural support for capabilities is that we can use them as essentially regular entities where they can be stored in registers, stored in memory, sort of manipulated in the same way how we would manipulate pointers. We can derive new capabilities from existing capabilities. but there are some rules that maintain the safety of capabilities. So in particular, if we're deriving a new capability from an existing one, we can only narrow the capability, but we can't make it wider, right? So obviously, if we can just blow away the bounds limits of a capability, this would be a way of circumventing the guarantees that capabilities try to give us. And the nice thing is, since capabilities are enforced by the hardware, this doesn't really rely on support from other privileged software layers like the OS kernel or the hypervisor, because this is simply an ISA mechanism. There are obviously some drawbacks here. So we now need to deal with an ISA extension. So there are new cap-aware instructions that we need to use to dereference capabilities and manipulate capabilities. So typically compilers can generate those instructions for us, but we at least need to recompile an application to generate capability instructions. And for some applications, that is not a fully automated process, right? So think about code that, for example, directly does pointer arithmetic. This is not something that would be safe under a capability model, right? So the compiler essentially doesn't know that this is safe, so that means manual porting. So things like memory allocators often need to be manually ported to be supported by CHERI. But what sort of attracted us to this hardware feature? Well, so obviously the ideas around memory capability support in hardware have been around for a very long time. What we didn't have were actual hardware implementations. And this is sort of one of the things that have changed recently, where ARM created something called the Morello platform, which is essentially an ARM implementation of the CHERI ISA. And so this was then made available to a bunch of universities. So we got our hands on an actual CHERI implementation, which meant that we could actually run systems that implemented sort of some of our ideas how CHERI could be used to support isolation and sharing in a cloud stack. And so the interesting thing about the entire CHERI ecosystem is that there's also quite a reasonably mature software stack for using CHERI in terms of compiler support, a FreeBSD version that is capability aware. There's ongoing work on a Linux port. So there's sort of quite a rich software ecosystem that you can also use when you want to experiment with CHERI. In addition, there are obviously FPGA implementation, software emulation. There are also CHERI ISA extensions for other architectures, including RISC-V. So there's, in particular for RISC-V, there's quite a bit of interest on adding CHERI capabilities to RISC-V. And there's a working group that is looking into this. And sort of more recently, we've seen interest in the embedded space, where embedded RISC-V versions were extended to support CHERI capabilities, now having 64-bit capabilities. And this is interesting for architectures that otherwise may not have an MMU and may not give you any other form of memory protection. If you're then adding capabilities to that architecture, you essentially get sort of compartmentalization, a lot of the techniques that I was talking about. So again, like there seems to be interest in exploring where these types of technologies can sit. Okay, so now let's have a look at sort of how we approach those two problems of combining isolation and sharing with a small TCB. So we first thought that we want some kind of compartment abstraction that is implemented using capabilities that would be useful in a cloud environment to deploy, for example, microservices or other types of application components. And we had sort of a couple of challenges that we wanted to address. So first, we wanted to support capability unaware software. So we didn't want to force everybody to port all of their software to a CHERI capability model just to run it within our compartment abstraction. We had to provide OS functionality in those compartments with a small TCB so that we could take existing POSIX microservices, Redis, and just deploy them. And we wanted to have efficient sharing, right? And we wanted to do that sharing through IPC-like interfaces again, minimizing the amount of porting effort that we would have to do if we wanted to, say, deploy a bunch of microservices on a single host in those into those capability compartments. So the abstraction that we came up with is something that we call cVMs, and you can kind of think of them as a hybrid of containers and VMs in terms of their feature set, even though they work very differently from either. So how did we deal with those three challenges? And I will talk about this in a bit more detail. But for the capability unaware application support, we essentially exploited something that is CHERI's hybrid capability mode that allows you to combine capability and capability unaware code. For the small TCB with OS support, we essentially went for having a per compartment library OS that then provides the specific system support that compartment requires. And then finally, to implement the data sharing, well, we had something, we had to have something in that software stack that is privileged, and we call this the intravisor. And that is essentially the TCB that we have, and that exposes an IPC-like API so that we can create, for example, asynchronous buffers or a file-like abstraction that then allows different cVMs to directly exchange data with each other. So I'm now going to talk about those three contributions in slightly more detail. So how does the support for capability unaware applications work? So in CHERI, you have two types of instructions. You have sort of your regular instructions that are cap unaware, and then you have your capability instructions that then only operate on capabilities and enforce the constraints. But you can also combine the two using something that is called CHERI's hybrid capability mode. And what it does, it essentially allows you to run native code that is cap unaware, but it constrains that code using a set of default capabilities. And those default capabilities live in a bunch of registers. So if you, for example, have a regular load instruction in your native code that then tries to access memory that is outside of that bound of those default capabilities, the hardware will reject that particular access. But at the same time, nothing stops you from using a capability instruction to access memory outside of those bounds imposed by the default capabilities, well, once you have access to that capability. So you can see that this is sort of exactly what we wanted, that we can by default constrain code to one of our capability-based compartments. But for example, for some of the additional mechanisms that we require, such as efficient sharing across compartments, well, we use cap instructions to then break out of those bounds and allow access to buffers, say, that live outside. So in terms of the small TCB, so as I've mentioned, we simply assume that we have a particular application with all of its library dependencies. So for example, libc and so on live in that compartment. And in addition, we also have a library OS that sits in that compartment, and that provides sort of other types of POSIX abstractions that that particular application requires. So here we used a library as based on the Linux kernel ported to user space, but we also experimented with other types of library operating systems that we could simply put inside of a compartment. So the interesting thing is that because we're using capabilities here, we can also provide some protection across those components within the compartment. And so here we have essentially something that looks a bit like a syscall layer between our application and the library OS. And then if the library OS needs to interact directly with the hardware, so for I/O operations, it then needs the help of the intravisor, and we have a separate host call interface. And both of those interfaces are also protected using capabilities. The caller essentially requires capabilities to invoke particular interface operations, so we're essentially also protecting that interface. In terms of deploying applications, it sort of therefore looks a bit like the types of cloud deployment models that people are used to in terms of sort of sticking things into a container image or a VM image and then deploying it. So cVMs are essentially represented as a disk image where you put sort of regular cap unaware binaries with sort of regular dependencies, and you can then deploy them on top of that intravisor that then can launch binaries within from that image that then have essentially a regular POSIX API. So despite the fact that we sort of are deploying multiple things that are isolated, all of those cVMs then run in a single virtual address space, right? Because the isolation is not implemented through page tables, but simply based on the capabilities that those compartments are given. And then finally, how do we handle data sharing? So here our requirements were that we wanted to have interaction between cVMs without really having a privileged intermediary on the critical path. We wanted this to work with cap unaware code, and we wanted to have an API that looks like a POSIX IPC API, again, to limit porting overhead. So here, the idea was that we had to somehow deal with the fact that we wanted native code that is cap unaware to be able to, say, access a shared buffer that is shared with another cVM, but that access would require capability instructions, right? So there's sort of a tension here, because normally when you're, for example, using shared memory and you're mapping pages across address spaces, once those pages are mapped, you can use, well, regular instructions to access that memory because it's just regular memory. But in our case, if we have capability unaware code, it wouldn't be able to directly access a capability buffer because it would have to use capability instructions, right? So obviously we could now have some compiler trickery to make this happen. But instead, the design that we settled on, we said that that shared memory that we're now creating across cVMs would actually be maintained by the library OS. And the library OS is something that we can make cap aware. So therefore, the access that is performed by the libraries can use capability instructions, and what the application would use implemented in native code is essentially some other interface call into the libraries to manipulate that particular shared memory that we have. So we then provided different abstractions for doing this. So something that looks like a file abstraction with reads and writes that we can support. We have a way of actually transferring execution from one cVM to another using a call like abstraction, where we are calling a function that then lives in another cVM. And then we also have sort of some richer synchronization primitives that we build on top of that. So because all of the interaction goes via the libraries, there's sort of often an additional memory copy that we need to pay as a cost compared to sort of direct access using capabilities. But that's the price that we paid for supporting cap unaware code. So all of that sharing is then mediated by the intravisor. So the intravisor is the privileged component here. So for example, if two cVMs want to share memory, well, they need to obtain, their library OS needs to obtain new capabilities that it didn't have before to access memory that lives in another compartment. And those new capabilities, they are manufactured by the intravisor as a privileged component. But the good thing is that ultimately, what the intravisor is doing here is sort of fairly limited in terms of functionality. It just needs to give that new capability to the library OS, and then it's no longer involved in any data sharing that then happens across those two capabilities that we have. Okay, so that's sort of the general idea behind cVMs and they work. I mean, I want to share one evaluation results just to show you that this is sort of real and it's something that we can run on actual hardware, and we've done sort of various experiments with this. So this is one experiment where we deployed a bunch of microservices using cVMs. So we ran Nginx and Redis, deployed in separate cVMs, and the workload were CSB queries that were executed against those microservices. And what we did here is we compared a deployment using cVMs and a more traditional deployment using Docker containers for those microservices. So for the deployment using Docker containers, the interaction between the containers was sort of the way it would normally work, by going via essentially a TCP/IP stack to interact. Whereas for cVMs, we changed that particular part of Nginx and Redis to instead use our IPC API between the compartments that we had. So here, what you can see in this plot, it's a throughput latency plot where we sort of increased the rate of requests and we measured the latency. And this is sort of for different types of queries in that YCSB benchmark. So the details don't really matter here, but as you can see, it has the green lines for the cVM deployment and the red lines for the container deployment. And you can see that the green lines are sort of shifted towards the right. So we essentially achieve a higher request rate before the latency increases, right? And sort of depending on how you look, there's sort of a significant performance improvement that we get because we can now enable the communication between those isolated instances more efficiently using capabilities. And also we do this while ultimately isolating those microservices more strongly than what we would have with sort of traditional container-based isolation that relies on namespace separation within a shared kernel, right? So this is sort of one demonstration of the potential benefit that we can get when we design a cloud stack that supports these particular features more effectively. Okay, so this sort of looked at that isolation and sharing part. So the second part that I would like to talk about is how can we increase memory density using capabilities. So here we really want to share particular components safely. So in this example of deploying a bunch of microservices using cVMs, there will be quite a number of shared components within those cVMs, right? Like, for example, database instances, a libc library, the library OS itself. So instead of sort of having this memory duplication, what we wanted to do is sort of take out those shared components and have both cVMs use them, essentially, therefore reducing the overall memory demand. And so as we know, this is a real problem, right? So when you look at modern microservice deployments, there's so much memory redundancy. So one particular benchmarks, the Death Star benchmark for microservices, when you sort of deploy some of those benchmark workloads, you're going to create a lot of MongoDB instances, right? And each MongoDB instances sort of potentially brings in large binary sizes, and there's sort of a lot of processes that are involved. So you'll have a lot of memory deduplication across your entire deployed microservice graph. And if many of those microservices are deployed on a single sort of large virtualized server, well, this is where you have a lot of memory redundancy. So what do people do about this today? Well, so one particular technique that exists at the hypervisor level, so if you use, for example, VMs to isolate different services that you're deploying, so one technique here is KSM, kernel same page merging. So here, the way to think about it is really the hypervisor now looks for duplicate pages, right? So it scans memory, it computes hashes over memory to identify pages that are the same. And whenever it identifies these types of pages that are duplicated, well, it can simply merge them by changing the mapping, where essentially a single physical frame is then mapped into multiple address spaces to remove that duplication. And KSM is sort of something that runs periodically and then removes those duplicate pages. So as you can imagine, like any type of runtime solution like this has a lot of tuning parameters, right? You need to decide how often is this going to deduplicate my memory, and which particular pages am I going to deduplicate. So therefore, KSM is something that in practice can be quite unpredictable in how effective it is, right? Because it sort of depends on a lot of those, well, non-deterministic parameters when you're running applications. And this is also something that we've observed when we experimented with KSM in KVM, is that you may have one KSM run that really reduces your memory a lot, and you may sort of redo that experiment, and then you suddenly see far less benefit that it achieves, right? Because it sort of depends on the precise memory layout that you have. It's also something that adds quite a bit of overhead, right? Because you're now, well, consuming memory bandwidth, essentially just computing hashes over pages. So we've sort of seen that you're sacrificing an entire core when KSM is running, looking for those deduplication opportunities. So something that is quite high overhead. I mean, also it's a mechanism that is entirely hypervisor controlled, right? So sort of the tenant doesn't really see that, except that they may notice the performance impact, but they have no control over, for example, which particular software components are being deduplicated, right? Because like the KSM mechanism has sort of no visibility of software components or services, because it simply does it at a page granularity. So instead, what we wanted to do is kind of take advantage of those lightweight capability-based compartments that we can create. And so we asked the question, well, so we have an understanding of what the semantic components are. Can we just share the binary data associated with those components using capabilities? And this is sort of the basic idea, that we're essentially creating finer grained cVMs. We're now taking out the particular components that we want to share, like, for example, a database instance or the libc library or the library OS, and we're just making it a separate cVM, right? So this is where we're really exploiting the fact that despite the fact that we're calling those things cVMs, they're not virtual machines, right? They're really lightweight entities, because they're just sort of, well, memory regions, right? So therefore, we can stick the library OS into a separate cVM, and as long as we give other cVMs the right capabilities to access that code, they can essentially do this with virtually no overhead. So therefore, we wanted to do this more fine-grained decomposition, and this way deduplicate our stack. So there were sort of some challenges that we had to overcome doing this. So first of all, we wanted to achieve this without increasing the TCB. And sort of one particular challenge here is that binary loading, ELF loading, is something that is actually quite complex. So if you're now sort of loading something to share it, and you're putting the loading in your TCB, that would make your TCB quite big. So we wanted to avoid that. And the other challenge is that obviously from a safety point of view, what we are sharing needs to be immutable. Because as soon as we allow somebody to change what is being shared, well, this will affect sort of everybody who's sharing that component. So that is bad. So therefore, anything that we're sharing needs to be immutable and integrity protected. So how did we deal with those two problems? So the idea with enabling these shared objects with a small TCB is by making the loader entirely untrusted. So the way it works is that a cVM first loads whatever object it wants to share, right? So it loads it, it does sort of, runtime linking. So once the object is loaded, only then it registers it with the intravisor as an object that it actually wants to share. And all the intravisor needs to do is create a new cVM and copy that binary object that is now already correctly loaded. And that becomes now a new compartment that is the actual compartment that is going to be shared, right? So all the loading part was done by an unprivileged cVM. And so now the sharing is done by other cVMs essentially requesting a particular hash of a component that they would like to access, right? So for example, cVM2 here can ask the intravisor, well, has that particular component already been loaded by referring to its hash? And if it has, it essentially obtains the capability to access the binary code directly from that shared cVM. So how do we deal with the second challenge, the immutability? Well, so the difficulty here is that obviously code is immutable, but we have other data segments with variables that are actually mutable, and they are required. So here in this example of sharing a database instance, well, we can share the code and the read-only data. But for example, what about a data segment where we have global variables or sort of anything else that is associated with that particular binary, but it needs to be mutable, and we need essentially per instance state. And so this is where we're then ensuring that this is now stored with the cVM that is actually sharing the code from another cVM. So we have something that we call compartment local storage, or CLS, that is then instantiated in the cVM that accesses another cVM. And then any, for example, global variables will be then stored within CLS, and therefore each cVM gets their own separate instance. So this is now implemented using some compiler trickery. So we need an LLVM compiler pass to essentially kind of change the sections and make sure that any sort of access to global symbols will then go through a function so that it is then answered by CLS as opposed to sort of the original section in the object that we are sharing. So there's sort of some complexity here to make this work, but it's sort of a way of then maintaining that property that everything that we put into the shared cVM that contains the database code becomes immutable. Therefore, if we compute a hash over it, that hash is never going to change. So I want to finish with one performance result on this. So we essentially deployed a microservice that does video transcoding using the FFmpeg library, and we wanted to deploy lots of instances of that service supporting a larger workload. And sort of each instance kind of contained the same code. So there's quite a bit of duplication for each one of those workers that we're running, to the point where the machine would be constrained by the amount of memory that it has when spawning those workers. So this was kind of the baseline deployment where we would use separate containers for those without any sharing, and then with sharing using KSM. So where the hypervisor would simply try to merge pages between those containers. And then our deployment with org, well, we would have the semantic sharing where essentially the FFmpeg binary and its library dependencies would be shareable by org. And so what we've now done is we essentially sort of started increasing the workload where the system would launch more FFmpeg instances. And what we were interested in is sort of what is the maximum number of instances, i.e. the peak workload that we can support before running out of memory. So with the KSM deployment, you can see that sort of the time slowly ramps up where more FFmpeg worker instances can be launched. It sort of happens slowly because KSM is working in the background, essentially going over memory, identifying pages that can be deduplicated, freeing up memory, and when more memory becomes available, more worker instances can be added, right? So eventually we sort of get to this peak number of instances, and there are periods when the number of instances stays flat because KSM is not running, right? So it periodically runs in the background and it sort of auto-tunes itself how often it should run. So you see this kind of behavior. In contrast with org, we immediately ramping up to 143 instances, right? Because we immediately know what it is that we can share. So there is sort of no background task that tries to deduplicate memory. We end up running a lower number of instances. So why is that? because org only shares binary data, right? Whereas KSM can also share writable pages that happen to be the same. So it essentially identifies more memory that can be deduplicated, therefore ending up with a higher number of instances that it can support in this experiment, but it takes a much longer time for it to get to that point. So it's kind of an illustration of the trade-offs between those two approaches. All right, so with that, let me conclude. So what I try to do in this talk is convince you that there is this interesting trade-off between isolation and application performance when we design cloud stacks, right? So we want strong isolation, but at the same time also efficient sharing. And so there is an opportunity to really step back and think, okay, if we now designed a software stack with new hardware features just for that, what would it look like? And what we've done, we sort of took one particular hardware feature, memory capabilities, and we thought sort of what would be new types of abstractions and mechanisms that we could design to achieve those requirements. And what is kind of interesting that we ended up with creating something where we could even run existing software, and it sort of started looking not that dissimilar from the types of cloud abstractions that people are used to today, but internally in terms of the implementation, it worked very differently. And I talked about the two examples. So cVMs is something that gives you strong isolation with data sharing, and org is sort of as a new way of doing memory deduplication across otherwise isolated compartments. Okay, so with that, let me finish here. So thank you very much for your attention. I'm very happy to take any questions. Thank you.
Thank you, Peter. I'll take this opportunity to advertise the next BCAS that will happen in 2 weeks on the 2nd of May at 6 p.m. Central European Time. We're going to have Oscar Menzer from Grok, who will be talking about programming their LPUs without using IEEE floating points. And now we will go to questions, and I can already tell that we have one question from Timo, so you should be able to unmute yourself now.
Yes, hello. Thanks for your talk. Very interesting topic. I have a couple of questions regarding basically your intro claim. So you say here that you have a small TCB, and we saw that you have actually a lot of things going on to enable what you just told us about. Do you have an estimate, like how many lines of code is your TCB? Of course, that's kind of hard to say, right? Because it also includes probably Verilog code or something like this to actually implement this ISA. But do you have some sort of comparison?
Yeah, so I can talk a little bit about this. So this is a good point, because I guess there's sort of a difference between what we would like our TCB to be, or sort of what it should be as part of our design, and what it really is in terms of our implementation. So I guess, so obviously on the hardware side, there are the CHERI ISA extensions, right? And they add new instructions and they change the architecture. And obviously we assume the correctness of the CHERI hardware implementation. Then in terms of the software TCB, we really only thought of the intravisor as being privileged because it essentially gets a root capability when we start the system, and therefore it is powerful enough to give out any other capabilities that we need to create, say, cVMs. So for example, if you want to create a new cVM and it needs to have memory allocated, you need to talk to the intravisor to obtain this. But it's
true, but what about the compiler pass, for example?
Okay, so there is also the compiler in terms of the translation of code to use capability instructions, right? So here in this picture, you also see the host OS shown as part of the TCB. So here we use CHERI BSD. So our intravisor runs on top of CHERI BSD. So obviously CHERI BSD is big, but it turns out that we're using CHERI BSD as a host OS mostly for convenience, because it's something that we could use out of the box. but we're not really relying on most of its functionality, right? So including like things like, I know, thread scheduling and so on is entirely done by the library OS that we have that is not privileged because it runs within a compartment, right? So here I think the host OS could be really shrunk because we need it for, well, supporting I/O calls and any other direct interaction with the hardware. So I guess to answer your question, that in our current implementation, this TCB is much larger than that it would have to be, especially when you look at some of the host OS code. But there are costs in terms of the hardware extensions and the compiler paths that you need to worry about. Yes.
And then my second and last question, if I may, in the very beginning, you showed a statistic, I think, of all the CVEs in, I think it was Linux, and kind of a categorization of what kind of bugs they were kind of exploited there. How many of these do you think CHERI solves? Because there are obviously some where using CHERI or not has no impact, right? If I write my database such, or my front end to my database such that SQL injection is possible, the same SQL injection will be possible if I use CHERI.
Yep. No, that's a good point. I mean, so like the ones where we can be effective is anything related to memory safety, right? So mostly spatial memory safety. So even temporal memory safety becomes tricky, right? I think there are things where capabilities can help, right? And this is sort of ongoing research where people ask the question, how can we achieve temporal memory safety using capabilities? But it's not that simple. But even when you restrict yourself to spatial memory safety, there's sort of there are quite a number of vulnerabilities that at some point rely on the fact that you can do an out of bounds access or sort of any other like memory safety weakness, right? So I mean, I think sort of.
So I think that is my question. How you see this space evolving, right? So of course, at some point, buffer overflows were the only attacks that basically people focused on.
Yeah.
What I'm thinking, and I'm no expert here at all, but from my perspective, how it looks like is that there are already so many mitigation strategies towards memory, or the exploitation of memory bugs at least, and I would say your system is one of them, that many attacks now go towards like the protocol level and things like that, where this doesn't help. So I would really like to see some sort of statistics, how this is evolving, right? Is this protecting me against 10%,
yeah,
90%?
So I think this is a really important point, and I guess so I don't have statistics, but I guess I sort of want to provide the context that, like, when we did this work, we didn't think of CHERI as simply a technique for helping with memory safety, and we want to, I know, solve buffer overflows. So to us, the question was really about creating very effective, lightweight compartmentalization. So if you now have software stacks that really embrace compartmentalization, how much is that going to help with security? And I think that is an open question, right? That intuitively people think, yeah, compartmentalization is a good thing and it helps with security. But we are not we don't really have ways of quantifying the security benefit, right? So for example, if I have a lot of fine-grained compartments in my software architecture, is it now more secure than having coarse-grained compartments, right? So to me, the question is, if we now think of software ultimately as being something that is compartmentalized by default, how is that going to impact security? And then it's not just about spatial memory safety, but for example, things like, I know, control flow integrity, right? So can we then ensure that if somebody breaks control flow integrity, this is restricted to a single compartment as opposed to them now being able to take over and hijack the integrity of another compartment as well, right? So I think it becomes a harder answer because since we don't have these types of architectures that embrace compartmentalization in this way, we also don't have enough evidence of how effective it is. But I think this is probably what is missing here.
Yes, thank you.
We have another question from Artira, I think.
Yeah, hi. Yeah, can you hear me?
Yep.
Yeah, hi Peter. This is Aritra from Huawei Zurich Research Center. Great talk. Yeah, quick question. So this is mostly from this loader that you talked about in slide 34, I guess. Because you said that the loader can be completely untrusted, right? Where you essentially load the binary and then, yeah, exactly. Yeah, so the problem here I could see is that so during the linking process, so how do you prevent the untrusted linker to link to a binary which is controlled by the attacker? Because you essentially don't measure anything.
Yeah, so this is a good question. So when you're linking the binary that you're loading in cVM1, you can only link to things that exist within that cVM, and that then also needs to be copied into the shared cVM, right? So because essentially, well, you need capability access to whatever you want to link against, right? So either through sort of explicit capabilities or default capabilities. So you can't link against anything that won't be part of the shared cVM. And what is part of the shared cVM, that is what is being measured here.
I see. And just another last question. So this is basically the next slide. So you talk about keeping the separate copies for the shared objects, right? To make sure that these are kind of private variable. How do you make sure that they're gonna merge in a correct way? Because at a point, for example, you may need to merge the database object to make sure they are kind of transitioning to a stable state, right? So how do you make sure that they're gonna merge in a correct way?
So in this example, you should think that the analytics microservice and the storage microservice, they want entirely separate database instances, right? So therefore they are like opening a separate database file. So they're completely unaware of each other, right? So therefore you want complete isolation and therefore they need to have their own private copies of any state associated with a database instance, but you're not worrying about sort of ever putting it together. Does that make sense?
Yeah, that sounds good. Thanks.
Good. If we don't have any other questions, I will ask a question. So you talked a lot about isolation, right? So you talk about those trustworthiness that we get very nice properties with CHERI. Do you maybe know cryptographic capability computing, C3? How does CHERI compare to that? What are the major sort of differences that you would see apart from the fact that it's encrypted, right? Because for them it's all encrypted. So is there something that you see that, for example, for CHERI you would be able to achieve, but you wouldn't be able to achieve for C3 and vice versa?
Mm-hmm. Yeah. So I guess the way I would think about this is that, yeah, capabilities are kind of a very overloaded term, right? And obviously capabilities are, well, access control mechanism, right? So we all sort of learn in introductory security class that you can have either capabilities or access control lists to kind of express and enforce access authorization policy. So CHERI capabilities are simply a very low-level form of capability that only encode access permissions to particular parts of memory, right? That's all they do. As soon as you sort of want capabilities that are richer, right, that encode other types of permissions and like this is sort of how capabilities are often implemented in software, right? And then you also have that problem, well, how do I protect those capabilities? So you can do it, for example, using cryptographic means, where you can still give a capability to a principal, but they can't tamper with that capability to, for example, give themselves more privilege than that the capability originally gave them. So I suppose the main difference that CHERI has to a lot of those other capability-based implementations is that because these are very low-level capabilities, they can be enforced and managed by the hardware, and that results in lower overhead, right? Because as soon as you sort of have software-based capabilities that now need to be checked, for example, in software where I know a hash needs to be verified, well, that will be a runtime overhead on the critical path, right? Whereas with CHERI, it's done by the hardware, so therefore you can kind of reduce the cost to almost zero, and that sort of means that they become applicable maybe in scenarios where otherwise you wouldn't have considered them, such as checking them on every single memory access that you perform.
Makes sense, thank you. Do we have any other questions? I think not. So thank you a lot, Peter, for your presentation. And I hope to see you all in 2 weeks.
Thanks a lot, everybody. Thanks a lot. Cheers.
Bye.
Bye.